Hello chaps, how are you doing? Well, this is like supposed to be the peak, my favorite lesson. I've been waiting for a long time for it. And no one's here, I'm alone, which is a shame, but never mind, I will get over it. Anyway, it is a really cool lesson. In my mind, it just brings out so many things. We're going to have matrices, we're going to have linear system, we'll have the determinant, we're going to have graphs, geometry. It is really cool. It also is a little bit difficult, but I don't think it's a huge part of the syllabus. It's part of it, so we'll go. If you don't completely get it, it's not the end of the world, okay? But it is really cool and interesting. So in page 142, and we're gonna do a geometric representation of our system of linear equation. See, the thing in maths is that everything is really connected. Everything is really connected. So you could be doing something in graph theory, and really it's matrices behind here. Okay, so everything can be kind of studied from very different topics in maths, and it's really cool to see sometimes it comes together. Right, we'll start with this equation. System of equation, and actually what we're going to start here is we're going to see where things are wrong, and I already hinted towards it. I said actually some systems, some linear systems actually are a problem. They might not even have a solution, or maybe they have too many solutions. So let's look at that, and you know, the easiest thing will be to use elimination or one of those things, but actually let's use the way we learned to do it. So what did we learn to do? We know that if I have, I'll write it down again here, it's nice to develop it once in a while. If I have a system, a linear system, okay, a bunch of variables, I know that another way of writing it is using the matrix of the coefficient, okay? So it's a nice fat matrix times the column of the variable x, y, and I have z, and I can go even more variables. Okay, and that's going to be equal to a column what I call the column of solutions. Okay, let's call them today A1, A2, and if you have 3 and so on. So every linear system, okay, a system of linear equations, okay, with certain variables can be written as a matrix equation like that. And we learned that we can find a solution simply by finding the inverse matrix, multiplying it on the other side. And then we get that the variables, okay, are basically equal to the inverse matrix times the column of solution. Okay, so that's the whole thing really of linear algebra. That's the main thing anyway. Now, where was I going? All right, so it's just really the whole trick is to find the inverse matrix, and we had a few different ways of finding the inverse matrix. I think the first one we came across was the inverse matrix is equal to 1 over the determinant of A times the adjoint, okay? The adjoint of A. And I'm not going to remind us how to find the adjoint of A, that's very difficult, okay? Now, what can go wrong? Well, something can go wrong, okay? Yeah, let's try with this system, okay? I know that A, okay, what is this matrix of the coefficient is 1, 1, 2, 2, okay? That's the matrix of the coefficient. So if I want to find the inverse, I'm actually not going to find the inverse. You'll see we're going to run into trouble straight away. You might even see it, okay? To find the inverse, I first of all need to find the determinant, okay? So let's find the determinant of it. That's very easy on a 2 by 2. It's 1 times 2, 2, minus 1 times 2, 2, 2 minus 2 equals 0. Okay, and by now I'm hoping you realize, yeah, we have a problem, okay? Because we're doing 1 divided by the determinant of A, but the determinant is 0. So what is the 1 divided by 0? We ran into big trouble, okay? So another title I was thinking of writing for this lesson, you could say, is what happens when the determinant is 0? And the answer is we run into trouble. So we need to figure out what kind of trouble it is. And I think to understand what it means, okay, let's just try and solve this linear system. And I started with 2 by 2. We're going to move on to 3 by 3 later, but 2 by 2 is easy, so we can see what is the problem. So I've got these two equations. I'll call them, can I stand here? Yeah, I'll call them equation 1, equation 2. And I think what I'm going to do 2 times, let's, instead of 1 and 2, let's call it A and B. Okay? So I'm going to do elimination, right? I'm going to get rid of that x. I'm going to do 2 times a minus b. Okay? So 2x, that will be 2 times that. Okay, so 2x times 2x, okay? That will be 0. 2 times y minus 2y, that's also 0. And then 2 times 1, 2 minus 3 equal minus 1. But what does that mean? 0 equal minus 1. Okay? That doesn't make sense. Of course it doesn't make sense. Okay? Right? So that means that this linear system, this system of equation, 2 variables, does not have a solution. Okay? So I'm kind of, poof, bursting your bubble maybe. Okay? Some systems, linear systems, don't have a solution. Now let's try and really understand, and some of you already maybe realize why there is no solution. Because look at these two equations. I mean, what is x plus y? And here I have 2x plus 2y. I mean, this left side is kind of the same, isn't it? All it is I double this. I double this side and I get this side. But if I double 1, I don't get 3. So of course, there's never in the world I will never be able to find an x and a y that if I add them, I'll get a 1. And then if I double, because what is 2x plus 2y is 2 times x plus y. It's never going to be 3. There are no two numbers like that in the world. Okay? So that means that the determinant, in this case at least, this case, means that there is no solution. Okay? So determinant giving you 0 means possibly no solution. You can kind of get, from my feeling is, that there might be a different situation as well. And there is. Okay? Look at this. If I change, what can I change here in this system of linear equation? Change just one number to bring out a solution, and even more. Okay? If I change this 3 now into 2, okay, will there be a solution? Of course there will be a solution. Okay? For example, I can choose x equal half, y equal half. Okay? Well, in the first equation, half plus half is 1, yes. Okay? Then 2 times half is 1, plus 2 times half is 1 again. So 1 plus 1 is equal to 2. Yes, so that is a solution. Okay? But is this the only solution? No. Okay? Let's choose another one. Okay? We'll call that x1, y1. Let's choose the x2. Okay, let's go with 1. x2, let's say x2 is equal 1. Well, in this case, what will y2 be? Okay, if this is 1, well, y must be 0, isn't it? So 1 plus 0 will still give you 1. But now let's see if it solves the second equation. Remember, these x and y's must solve both equations. Okay? So 2 times 1 is 2, plus 2 times 0 is 2. Okay, so 2 plus 0 is 2. So that is also a solution. Okay, by now I think you realize that there is more than one solution. In fact, there's an infinite number of solutions. Okay, for every x you can choose another y that if you add them together you'll get to 1. And that will automatically solve the second equation. Why? Okay, because equation B is simply double A. Right? If I double A on both sides, I'll get 2x plus 2y equal 2. So these equations are the same equation. Okay? I just wrote them in a different way, but it's the same equation. And you know that to solve a system of linear equation with 2 variables, I need 2 equations. But now, really, it's only 1. So I'm going to have more than one solution. Okay? Let me just show you what happens if I do, let's say I try and do elimination like I did before. So I'm going to do, what I'm going to do here, just like I did before, I'll do a 2 times equation A minus equation B. Okay? So 2x minus 2x is 0. 2y minus 2y is 0. 2 times 1 minus 2 is also 0. 0 equals 0. Yes. Okay? That works. Okay? But let's just think about it for a second. Okay, I'll just pause here just to make sure I get my points correctly. Okay, so we understand there's definitely a solution. In fact, there's more than one solution. So what I want to ask us, what I want us to think about is how many solutions there are. Now, we realize that these two equations really are the same thing. They're the same thing. So let's just try and express y in terms of x. Why am I doing it? Because I'm thinking, okay, maybe any x and any y will solve this system. But that's obviously not the case. I mean, let's say if x is 2 and y is 3, 2 plus 3 is 5. It's definitely not 1. So I can't choose any random x and y. There is some kind of rule. Let's try and find out the rule. So I'm going to just rearrange that to find out y equal 1 minus x. Or let's write it even better, minus x plus 1. Because that's how you write these things usually, okay? So, what does that tell you? This is the rule, okay? X can be any number. 1, 2, minus 0.2, minus 5003. Any number that you want. But for every x, you're going to have a certain y, and those pair will solve these equations. Okay? Now, if x can be anything, we said, then how many solutions there are? The answer is infinite solution. Okay? There are infinite solutions. Okay? So, we're going to see also, well, we'll see another thing there for a second. We'll pursue this for a bit more. But for now, let's just focus on like our first kind of main result here. Okay, we'll just pause here for a second. If I have a linear system with two variables, but it's true also for three, we'll see that later. If the determinant is 0, then either there are no solution or there are infinite solution. Okay? How can we tell if there are 0 or infinite? Well, you need to just try and solve it. Okay? In this case, when we try to solve it, okay, we got, yes, there is a solution. For every x, there's a certain y. Okay, so it's not no solution, therefore there must be infinite solution. Okay, so we just try and solve it. Okay, this was a 2 by 2, so it was really easy. But when it comes to 3 by 3, I'll remind you how we solve these things. But that's the same thing for 3 by 3. Now, what I want to do now is just... I'll just pause here for a second. Okay, where I want to take this, and we'll do that in a minute, is do what I said in the title, do the geometric representation for that. So that's where we're going here. We want to see what does it mean? What does geometrically, what do these solution means? But I think before I do that, I might as well, just to add to this, write down what happens when the determinant of A is not equal to 0. Okay, so let's say I have a different system of equation. I'll leave that here. I'll leave that here. I'll just pause and make sure I've got a good system so it doesn't mess us around. Yeah, okay, so I'm going to come up with a different system of equation. X plus y equal 1, same equation. X minus y equal 2. Okay, that should have a solution. But let's just see that the determinant is actually not 0. So what will be the matrix? Okay, is 1, 1, 1 minus 1. That's the matrix. That's A. Okay? Therefore, how do we find A minus 1? Well, let's just find the determinant, shall we? Okay. So I don't really want to find A minus 1. I just want to find the determinant of A. Because I want to show what happens when the determinant is not 0. I just want to show you that the determinant is not 0. 1 times minus 1 is minus 1. Minus 1 times 1, it's minus 2. So, okay, we've got a system here, okay, that has the determinant which is not 0. Now, let's see if we can solve it. It's just the old traditional way. Elimination, okay? I'm going to add these together. You can see you can easily get rid of the y. So, I'm going to have 2x equal 3. That means x equal 3 over 2, okay? And if x is equal 3 over 2... then y, if I'm not mistaken, should be minus half, right? Because 3 over 2 minus half will give us 1. Okay? So we have a solution. So what did I come? What's the conclusion? If the determinant is not 0, then we have, and I'll add this word now, we'll have a unique solution. Okay? So we don't just say we have a solution, we have a unique solution. Unique meaning 1. Okay? Right? So what does that mean, 1? Well, we have just one x and one y that will satisfy these equations. Where here was a different case, right? When the determinant was 0, and one possibility was that we have infinite solution. We can have millions and millions of x and millions of y related to each other. We can't just choose any x and any y, but yet we have lots of x and y's that fit the bill. So that is really probably the main part of this whole lesson. Okay? The second part is to go geo now. We're going to go geometric. Okay, so I'll clear some space here. Okay, so I've rearranged everything that we had. Not everything, but the most important thing. Again, we had 3 systems. We looked at 3 systems. Okay, the first 2 had a determinant. The matrix coefficient had determinant 0. And so the first one actually had no solution, but the second one also determinant 0. We actually had infinite solution. And then we have another system with determinant not 0, and we say we have a unique one solution. Now I want to understand, and it will make more sense when we're trying to analyze it geometrically. So what do you mean geometrically? We draw a graph, okay? We draw a graph. So I'm going to just put these Cartesian systems, okay? Because you know, each line, each equation, really, x and y, well, it's a graph, isn't it? For example, x plus y equal 1. We can write it as y equal minus x plus 1. Okay? This one, if I want to turn in terms of y, it will be y equal minus x plus 3 over 2. Right? I'll just move the minus 2x divided by 2. Yeah? Okay? Here, this is the same, obviously it's the same line. Actually, all of these are the same line. So that's y equal minus x plus 1. And this one is similar to that. Instead of 3, I had 2. So it's 2 over 2. So that's y equal, well, it's 2. So I'm going to move the 2x over there, then divide by 2. So it's going to be minus x plus 1. Can you see already what's cooking here? Yeah, we'll come back to that. Maybe it's starting to kind of all click together in your head. Okay, this one is the same. The first row is all the same. Minus x plus 1. This is a different one. So I'm going to move the y over there and the 2 over here. So it's y equal x minus 2. Okay, now let's see what happened. I should have done it in different colors, but never mind. Okay. Yeah, we'll say this is the blue and this is the red. So what I'm going to do now, I'm going to plot the graphs. Okay, there's 2 graphs for each system. Okay, we're going to plot them. I don't know, we'll see what happens. Y equal minus x plus 1. Well, that looks like this, isn't it? That's 1 as well, right? Y equal minus x plus 1.5. Well, it has the same gradient, so it's a parallel line, okay? And it hits here at 3 over 2, right? Okay, I'm not going to say anything. I'm just going to do them all, and then maybe already now you're starting to realize why. We're trying to figure out that why. Okay? Leave you in suspense a bit. I think some of you clicked already. This one, well, all these ones are the same, so I'm going to draw all that the same. Okay, that's the same equation. Okay? Right, what's the next one? Oh, okay. That's a bit funny. I've got the same graph. So I'm going to put the dot, just to see, so you can see they're on top of each other. Got one line here. I told you it's the best lesson, this one. Yo, so exciting. And this one, x minus 2, so it's actually going up. And it's crossing at minus 2 here. So it will be, I don't know, something like this. Okay, so that's 2, and that's minus 2. Ooh. That's a little bit different. So let's just use words. What's that? Forget about that. Here we have 2 parallel lines. No intersection. No intersection. They're not touching each other. Here there is 2 lines, but they're on top of each other. Infinite intersections. They're crossing each other all the time. Infinite. I'm using the word infinite intersection. No intersection. Infinite intersection. Here we've got 2 lines, different lines. Let me just put the line here. Maybe you can see it a bit better. Yeah, a little bit better. And these lines have, they're not parallel, okay? So they're intersecting in a unique, using that word, unique point. And now I think it all comes together, okay? Why do we have no solutions here? Because each one of the equation is represented by a line. And the line are parallel, okay? So they're not touching each other. So we can't have a joint coordinate, xy, which is shared by both these lines. So in other words, what is a solution? What is a solution? It's a coordinate, it's an intersection. It's a coordinate that both these lines will agree on, and they agree on nothing. Okay? Where here, okay, these two lines, there's one coordinate here in that intersection, which is a solution for both of these equations. Okay? So a solution really is an intersection. Okay? There's a unique solution here, okay, because they're not parallel. There are no solution there, and there are infinite solutions here. All x and y's, okay, well, not all x and y. For each x there's a certain y. Which y? This one, y equal x minus x plus 1. So there's infinite solution. Cool, isn't it? Okay? So now we're going to do the same thing, but we're not going to go through all the mechanics. We're just going to have to trust that these results are the same, but we'll look at them, the geometrical aspect anyway, in 3D. I think I'm going to do a different video because it's getting a bit long. Cheerio. Well, see you in a bit.